Now let's welcome Professor Huan Chen from National Zhongxin University. The speech is entitled Deep Learning and Federated Learning for Non-Intrusive Appliance Load Monitoring. Let's welcome.
Good morning, ladies and gentlemen. Thank you for coming and joining me with this session, either in the conference room or in online. Okay, today my name is Huan Chen, and I'm an associate professor with the Department of Computer Science Engineering and in National Zhongxin University in Taichung, Taiwan. Okay, I'm also a member of TWISC at the NCHU. Today I'm going to introduce a very interesting topic which is known as a non-intrusive load monitoring or non-intrusive appliance load monitoring. Both terms are okay. In this talk, I'm going to introduce what non-intrusive load monitoring is and why do we need it. And most of all, I will focus myself in the deep learning method and how to train a good model using a deep learning method. And in the privacy concern, we will also introduce the federated learning schemes which can preserve the privacy in use. All right, I would like to divide my talk into 6 sessions. First of all, I will introduce what the non-intrusive load monitoring is and why do we need it and what benefit we can get from using the non-intrusive load monitoring. In section 2, I will introduce the related work till now, both the conventional ones and the modern ones, which is designed based on deep learning method. Then we will come to the system design. To have a good non-intrusive load monitoring, we must have a system. So in this talk, both the hardware and software will both be introduced. In addition, particularly, there is a open toolkit called the NILMTK. It's a very good toolkit for implement the system. Next, we will focus ourselves in a deep learning method. Then the federated learning for privacy. Our emphasis is to show that using the federated learning method, we can greatly encourage parties to upload the high quality data to the data center. Finally, I will conclude my talk with several highlights. All right, let's talk about the why do we need non-intrusive load monitoring. To address the energy crisis, there are 2 approaches to address this issue. One approach is for the energy generation. We can generate more and more energies. And the other approach is that we can perform some tasks about the energy conservation. So these 2 opposite approaches, we can both contribute to our energy crisis. The first, in the left part, you can see that this is this is energy generation. In particularly, in recent years, because air pollution and warm effect for the air pollution, so many countries focus on how to generate renewable energy, which is a green power. So they can generate the power from the wind power, water power, and some solar power. According to the Renewable Energy Market report, which is done by International Energy Agency in 2019, it says that the global renewable energy power generation will have another 1,200 gigawatts till the end of 2040. So this is a big amount. So many countries are trying to generate more and more power. They focus more on the renewable energy power. And in this report, it also mentioned that we need to reduce the power consumption by increasing the efficiency, so that otherwise we still have some energy crisis. On the right-hand side, this is another approach. It's called power conservation. Power conservation is a good way to is a good way to address the energy crisis. Take the advantage of the AMI, Advanced Metering Infrastructure. We can have some smart meters installed so that a current smart meter has several functions that can help to preserve the energy to perform the energy conservation. Several functions, among them are communication reading, meter reading. So it incorporate the IT and into the power grid, so we can communicate two-way. The other is the dynamic electricity price. So we can incorporate both the demand side and the generation side. So we have the real-time information and the remote control inside. So we can use the energy more efficiently and more reliably. And in the research, in the service provided by the AMI and the current metering system, there is a service called the demand response. And the benefit from demand response is that it can optimize the scheduling for consumers and save more energy and to use the energy more efficiently. There are two ways to obtain the information. So the big thing is that how do we get the information from the users? There are two ways. One is the intrusive way. One is the intrusive way. So we can install more and more sensors and to transmit the electrical power and to the cloud. This is called the intrusive load monitoring. This is a very high cost because you have to install many devices in your home. The other way is to use a smart meter to collect the total power data and use our schemes called the non-intrusive load monitoring algorithm to analyze. This is a very cost-effective way. For example, our company has a Taipower. Taipower is the biggest company, and they have a smart meter installed. According to a report of the Energy Bureau in Taiwan, a smart grid promotion and the future planning, and they published in 2019. Taipower has actively installed the low voltage small meter in general household users. The progress is as follows. Now we have over 600,000 households have installed the smart meter already. And the goal is to install 1 million households by 2020 and 3 million households by 2024. In the future, people can use the home energy management system, which is installed at home, and we can provide more information. In the right side of this page, you can see that this is called e-counter application provided by the Taipower. Everybody can download the app from the app store. So it's available right now. So Taipower has actively promoted this. So right now you can see the usage of your home, but they do not install they do not develop the non-intrusive load monitoring yet. So it's a great opportunity for us to do this research. Then I will introduce what is a non-intrusive load monitoring. According to wiki definition, the non-intrusive load monitoring is a process for analyzing change in the voltage and current, and it can deducing what appliance you are using. In other words, non-intrusive load monitoring can perform the energy disaggregation. You can separate the appliance signature, the flows, so you can perform these functions. Our goal is to reduce power by raising the usage awareness. So if you can know the usage of your home, you will be aware that you don't want to waste a lot of power. This technique usually is promoted by the HART, a research called HART in 1992. So everybody follow its definition. And as you can see in the figure, its main goal is to disaggregate the power you use at home. So you can separate what is used by your refrigerator, your microwave, or other major appliances. So that our bill will not only a single line, the total bill. We can separate it. We can know everything about our usage. All right. In next page, I will compare the intrusive load monitoring versus the non-intrusive load monitoring. In the left-hand side, you can see intrusive load monitoring. You need to install the devices or the meters on each appliance. So they are called one sensor for each appliances. So it's a very costly, solutions. On the other hand, non-intrusive load monitoring, you have to install one sensors only in the manpower, so that it can disaggregate energy usage in your home. So it's a lot of difference. So why it is a very cost effective. Next, I will introduce the related work. Usually, the related work contains two parts: conventional ones and the modern ones. Conventional ones are usually divided by the signal processing and the state predictions. Here, I list several very typical research. The first one, like for example, the first one. Dr. King used the hidden Markov model to perform the on-off state predictions in 2011, and this is a very typical algorithm. As you can see, they are designed based on the signal processing and state predictions. So you constructed the hidden Markov model and predicted the on-off state for each appliance. And next, then we will improve the results by factorial hidden Markov model. The most important one point to mention that the first paper has more than 5,000 citations, and the second paper has more than 1,000 citations. So these two papers are very important to reference. Mr. Coulter also built a data set called REDD, Reference Energy Disaggregation Data Set, and they have several houses, and his targets to furnish further research on this field. And next, Dr. Zhong improved their results by developing adaptive factorial hidden Markov model and a signal aggregator 这个 constraint. So SAC is a very interesting one, and so it's get a very good result. All right, the fourth important papers is by Dr. Hsing. It has another UK DAO data set. So in this paper, it also compares several important algorithms like the machine learning, conventional schemes, and deep learning schemes. So it's a good paper to reference. It published in 2019. So once again, the related works for conventional schemes are designed based on the signal processing and the state prediction. On the other hand, we have a deep learning method. Deep learning method, as you can see, the deep learning method, they use the conventional neural network. This is a very popular one. Then, with the advance of the deep learning, we will go to the new good model called conventional autoencoder, and we also use this convolutional autoencoder. Then we have the recurrent neural network. Recurrent neural network is good at to process the time series data. Then we have the conditional variational autoencoder. You see that the deep learning has a lot of variants. So its development is very rapid growth. Then we have the sequence to point algorithm. Sequence point algorithm deal with the input is a sliding window. You can input a sliding window sequence, then output a single target, a single point for the target appliance. So it's very useful to deal with how long, or you don't have to concern with that. Then we have the multi-layer perception. As you can see, the multi-layer perception, you will deal with the state prediction. So we perform the energy declassification, on and off state. Long short-term memory is also a typical model in the deep learning. Okay, next, I introduced the non-intrusive learning toolkit. If you want to do this kind of research, you must know this to open resource. It's a open framework that can integrate third-party data sets. You can incorporate your self-collected data, and you also can develop your own algorithms. So it's a very flexible platform you can use, and you can put everything together. You have the hardware and collected the data by yourself. Then you have your own developed algorithm, so you can incorporate everything in this framework. It's a very helpful research. As you can see, this figure in the left-hand side, this figure is a NILMTK toolkit. In the left-hand side, you can see you can feed many types of open data set, like REDD, root, or our collected new data set into the same framework. Then there is a data interface over here, and everything gets into the NILMTK data format module, and they will put everything to the same format. Then you will have a statistics and the pre-processing module to perform some basic statistics and pre-processing, like a missing data or some duplicate data you can process at this pre-processing module. And you can develop your own algorithm and have the training data, model shell, and you have your own developed algorithm into it. Then you can have some utility function, like you can evaluate your performance. So the highlights for this NILMTK toolkit is that it has two default NILMTK NILM algorithm. One is a combinational optimization. The other is a factorial hidden Markov model. These two are very conventional ones, so you can develop your own. Like us, we develop our own deep learning model called conventional autoencoder, and it's some variations. And it also contains 5. It also contains 5 open data set. So inside this framework, sure, you can incorporate your own data set. So it's a very flexible framework. All right. Here then we come to the system design. If you want to collect the data, you need some hardware and software. How do we build our NILMTK? We share some experience with you. This is an overview of our system design. As you can see, the first part is the aggregator and the power surge, so that you have a hardware aggregator. I will introduce in the next slide in more details. First of all, you have to install an aggregator and a power surge. Secondly, you have to install the submeter per appliance. But this is for the benchmark only. For example, you want to know the label, you want to know the ground truth, you need to install the Submeter. But when used in everyday's life, household, you don't have to install this. Submeter, you don't have the Submeter installed when you use. But for training, we need do the research. You need to have some Submeter to know the ground truth. Our goal is to analyze the data from the aggregator only, so that you can know that whether your answer is the same as the value measured from the Submeter. The third part is the database. You have to put your collected data into a database, and we have a dashboard for visualization. And we have also have the NILM algorithm in the NILMTK framework. So you develop a new algorithm and use it to test whether your new algorithm is effective or not. So I have some highlights, system highlights in the left part. First of all, we have the aggregator. Aggregator has a wireless capability. Is using the ESP2266. This is a popular module, wireless module. And we also have the DSP module. It's called ADE7878. This is a very good three-phase measurement IC. So it have a high accuracy, and it has three phases. You can test. Then we have the Submeter per appliance. We have the database dashboard. We use the NILMTK framework to put everything together. We have collected our self-data. We also develop our own deep learning model. Then I will talk about the hardware we use. The first part is the aggregator. Aggregator is the devices you installed in the manpower. So as you can see, we use the Hall effect sensors. Hall effect sensors can detect the value of the current. So you can use the electromagnetic inductions scheme to detect the value of the current. So you install inside it. You have the wireless power and the ADE7078 module. So you can measure. You can have the measurement of the power. And this picture on the left, on this right-hand side is a check table for the measuring electrical power. Everything is inside it. Again, this is an aggregator installed in the power surge. And so this is a side view we install in the power surge, the main power surge. This is the Hall effect sensor that can detect the current, how much current you can get through this line. And everything gets into this box. And inside we can measure the power and transmit the measured power via wireless. The second part of the hardware is called Submeter. This is installed in every appliance. It's only for benchmark or for the ground truth purpose, so that you can compare the result disaggregated from the main power and compare the result from the Submeter you measured. So you can have the ground truth. The Submeter we installed, we use the DSI 5162 beta version. This is a Realtek Amoeba development kit. Is also a wireless module, and we have an ADC converter to convert the signal from the analog to digital. So this is small devices. Okay, as to the software, there is also a software we use, the NILMTK, which I introduced in the page 11, so the audience can reference the pages. So we put everything together, hardware and software, so that you can put everything together and to collect data and to perform the analysis. In sum up is that hardware collect the data while the software perform the energy disaggregation purpose. Then we will share some experience how we develop the deep learning and how to improve our performance using the meta heuristic inside it. Is a very good feature that everybody can use to improve your performance. For deep learning, we have to perform the data preprocessing first. We have several data preprocessing. First of all, we have to perform the data normalization. Data normalization is a process that can transform the value of the data in different range to a specific range. So that will help the converge of your model. So this is a typical one that we will use for the deep learning process, data preprocessing. The formula is very simple. The next data preprocessing. Since the signal is a long time series data, so we have to divide it into several chunks, several segments. So we perform a segmentation technique that separate the 6 data into a frame. So this segment and another segment, they don't overlap. Otherwise, we'll have too large data to process. So it's a very simple way to just segment them into small chunks of 600 data samples. Let's go to the main part of the model. We apply the one-dimensional convolutional neural network. This is one-dimensional convolutional neural network can extract the features in time series. So you extract the patterns that occurred in your time series. So there is a one-dimensional version. One-dimensional CNN is widely used in signal processing for the speech or for other time series. We also apply the one-dimensional convolutional CNN in our ECG data, which means that any kind of a time series data, you can apply the 1D CNN to extract the features occurred in your signals. So this is a one-dimensional CNN. It's a kind of long. You have you have a 600 data fit into your model, and the convolution layer and the transport layer into the other side. You can reconstruct the output. Then the other technique we use is the batch normalization. For a fresh student, they don't use the batch normalization to improve their efficiency. But I suggest that a batch normalization is a good processing that you should apply to your deep learning model. That will help your model to converge better and faster. The batch normalization advantage of applying the batch normalization has you can solve the gradient vanishing or gradient explosive problems because and you also can deal with the overfitting problem. So you must apply this in your training. Why we have the gradient vanish problem and the vanish explosive problem? Because we always use the gradient gradient descent to update our parameters, right? According to the partial derivative formulas, as you can see, if you want to perform the partial derivative to specific weighting, and they probably has a long chain rule, long terms because of the chain rules. So that is easier to have it's easier to have the gradient vanish problem or gradient explosive problem. That means, but the batch normalization can adjust the output, the distribution of the neurons to solve the above problems. As you can see, in several books or papers, they also have provided this information already, and this is we also prove that they can solve this gradient vanish and the gradient explosive problem. On the right hand side, as you can see, the bench normalization. This is the output of the weighting distribution, the distribution of the weightings. This is layer 1. It's fine. It's kind of evenly like a Gaussian. Then as the layer 2, layer 3, layer 4, and as you goes on, the range becomes smaller and smaller. So that it's not easy to train the model anymore. But applying the batch normalization, as you can see, at each stage we apply the batch normalization, so we can recover the distribution of each weighting. So as you can see, layer 1, layer 2, layer 3, layer 4, layer 5. So it's not, so we can mitigate the problem of gradient vanishing or explosive problem. The other things we use for in our model is to improve our performance is using the using the meta heuristic method. Thanks to the Hill-Kaimin algorithm they developed, this is a very good. This is a simple, the simplest one of the meta heuristic technique. Because you use the hill climbing technique, you can tune in the hyperparameter during your training, like the hyperparameter, like the learning rate, because the learning rate, if you set it too high or too small, it's not good for the training. If you set the learning rate too small, then your model will converge too slow. If you set the learning rate too large, they are falling into the local optimal. So the hill climbing algorithm is used to tune the hyperparameter. So that we prove that it's a very effective way. Then we can improve our performance even more. So the system model is look like this. The input is the aggregated data. So they probably have 3 or 4 aggregated appliances signals in this field, in these figures. And they collected in the manpower. Then you feed the power. You feed the data into your model, 1D convolutional neural network autoencoder model. Then get out. Then you will get the feature of a specific appliance. Apparently, the model for each appliance, you should use different model for different appliance. So it's a very interesting. This is the first one is the aggregated data. Then use for find some specific model. You can train for example, the microwave, then get out a microwave shape. So the right-hand side, you can show that we show that the dis-aggregation training results for the fridge is much better than other skin. The red lines, the lower the better, because the horizontal line is a loss. I'm sorry, the horizontal horizontal is the epoch, and the vertical line is the loss. The lower, the better. Our scheme is a red one. And we also show that our result is great on the microwave. Oh, it's very good. This page also shows our experiment result in more detail. As you can see, the figure A shows the aggregated data, and the ground truth of the fridge is shown in figure B. And this is the predicted fridge. So this is the output of our model. As you can see, the ground truth and our predicted one is very similar. And this one is the error. Their difference, you see, is very small. So this is a very great scheme to apply the deep learning with hill climbing method. Then I will give a short briefing on the deep learning with some highlights. A deep learning based on the energy disaggregation scheme we use the one-dimensional convolutional neural network model is applied. We use some training technique. In particular, they include the batch normalization and the hill climbing schemes to further improve our results. Finally, we compared the results using the open set data set, REDD, as well as our collected own data. We also compare the results with the factorial hidden macro model, combinational optimization, and the convolutional autoencoder, and the autoencoder with the hill climbing improvement. Okay, I will go to the next sessions. The second part of my talk is about the federal learning. When privacy issue is concerned, the original deep learning data is a big challenge because nobody wants to share their data due to the privacy issue. In this situation, Google developed a new framework called Federal Learning in 2016. Federal Learning is a good way that you don't have to upload the real data. You only upload the model. It's enough to collaborate the training. So it's a good way to deal with the privacy issue for the deep learning. What is federal learning for privacy? So when the privacy issue is concerned, traditional machine learning or deep learning that require big data is a big issue because you need the data for your training. In particular, for the deep learning, you need a lot of data, high quality data, but it's it's a very challenging for everybody to share their data with everybody. So for this privacy issue, in 2019, Europe proposed a data protection law. They have a law called the GDPR. They protect the AI data privacy. So you must you cannot use the data freely. You don't have to share. You have to consider the privacy issue. However, the high quality model training requires a large amount of high quality data. If they don't want to share, how can you get a good data? Without the good quality data, you cannot get a good quality model. So at present, many small companies, in practice, they have a good quality information, but they don't want to provide it outside the use due to the privacy issue. So to mitigate this problem, federal learning comes in, and it can solve which is so-called the data island problem, which means that nobody wants to share the data, so you cannot have a good training. So federal learning actually have three types. We use the first one called the horizontal federal learning. Federal learning, as you can see, the X stands for the feature space, Y stands for the label space, and the I stands for the data space. If you keep the feature space and the label space the same, but keep the data space differently, and we are in the mode of horizontal federal learning. This is the most widely used type. Other types are like the longitudinal federal learning and the transfer federal learning are used in other scenarios. So for our scenario, we use the horizontal federal learning. In the case, the federal feature space and labeling are kept the same. And federal learning can improve the communication. And some research issue has been proposed to improve the communication efficiency. One is the structural update and the sketch updates, which is out of the scope of this talk. So we only introduce how to apply the federal learning on the non-intrusive load monitoring schemes. Okay, you also can use the federal learning can operate in the encrypted domain, which means that even if you transmit not the data but the model, they also can encrypt it and upload this model to the center. And in the encrypted domain, they can operate like the averaging, something like that operation. And so in the center, nobody knows your privacy data. This is the structure of our horizontal federal learning. As you can see, everybody has one household, second household, and there's many houses. They have their own data. And they don't have to transfer the data up to the center. They only have to transfer the encrypted model to the center. Then in the center, they can operate in the encrypted domain. It's a very, very brilliant. Okay, based on the horizontal federal learning, all members use the local data to train the local model and upload their gradients, which means the model or the weighting. While in the global center, they merge the models so that they can operate in the encrypted domain. Data quality varies, so sometimes the low quality data may cause a poor model performance. So when we do the research, we observe this kind of situation. So we have several twisted the model, the federated learned model, as you can see. Under this framework, all federated members can get a better model effect. And even every time the global model is updated, and they can choose to use this one or their local one. We use the neural network model variational autoencoder. This is a more advanced model than our pre-mentioned one, aforementioned ones. Variational autoencoder is replace the CNN. It's a more advanced one. All right. For the privacy issue, use the homomorphic encryption, which means that everybody has the data, and the data we encrypt the data in the encrypted domain using the homomorphic encryption, so that allow the encrypted data can be operated in a to allow the center can merge the model in the encrypted domain. Homomorphic encryption is a form of encryption allowing one to perform calculation on encrypted domain. Okay, here we have several results, that preliminary result that you can show the effect using the data-centered or federated learning. The first one is that we have a data set. We send everything to the center. This is not federated learning. We just collect every data, distributed data, collect every data. So as you can see, we will get the best performance by doing so, because every weight you can tune the weighting for each tuning, so you get the best one. However, when the privacy is concerned, you have to encrypt your model. So you send the model instead of the data to the center in the encrypted domain, again in the encrypted domain. Then the decrypted, not decrypted in the center, you just operate in the encrypted domain using the homomorphic. Then this, like the averaging, then send it back. So each local data has the global global model. As you can see, the data center, you send everything to you get the best performance, lower the better. However, the federal learning weighting average, but it's an example. It's only an example. Usually has a poor in performance than the data centered one. How to improve that one? So we have several merge methods for federal learning. The most widely used federal learning schemes, merge schemes, is to perform the weight averaging at the center, which means that every party sends their own model in the encrypted domain, and we merge them in the center. The simplest one is to merge them by averaging. Then we will, however, the other good thing is that when they get down, we will compare their local one with the global one. Which one is better? So we will have a better result. As you can see, we will have better result. This federal learning selective averaging will have the best result. And we can improve the performance. Okay. We also shows that the local training can perform our federal learning schemes. Our federal learning selective scheme can perform even better than the local training scheme. Local training schemes means that you don't exchange your model with others. So our federal learning selective scheme can perform even better. Okay, let me conclude my talk with some highlights. Non-intrusive load monitoring is a very cost-effective solution because less devices should be installed, but it's a very challenging research due to its complexity when multiple appliances are in use at the same time. Federated learning can be used to train a non-intrusive load monitoring model to protect users' data privacy. Deep learning schemes are required or are reviewed. We have reviewed several deep learning methods, and in particular, we use the one-dimensional convolutional neural network autoencoder model with advanced training and tuning techniques with the meta-heuristic known as the hill climbing method to tune our hyperparameter learning rate. The system design with hardware implementation and a non-intrusive load monitoring framework is shown to which can greatly which shows that we can put everything together that help our potential, shows our great potential in our research. And federal learning framework is used to protect users' data privacy, and its variants we also discussed in our talk. So various federal learning merge algorithms we have compared, and the future research directions are suggested. Okay, this concludes my talk. Okay, thank you everybody for joining me with this section.
Let's thank Professor Chen once again for his inspiring speech.